So I know Yakir since this time, 2010. And at that time, our laboratory already was at Maryland and close to Washington, D.C. And when Yakir arrived to receive the medal, Jeff arranged our meeting, and we were with Yakir for receptions at National Science Foundation, at Office of Naval Research. And I was very, how to say, impressed how simple was Yakir's behavior. He wasn't surrounding himself by a wall of greatness. And it was the usual person, and we were discussing and discussing from the very first moment of our meeting. And I still keep the napkins which were used during the discussion of physics of superconductivity and quantum physics at this meeting. And this was even more impressive when we were at National Science Foundation, and Yakir said there some words which I remember until now. He said that when I am attacking some problem and trying to solve it from this angle, that angle, and eventually is getting solution, then I am telling how stupid I was. It was so simple, and it was. And when he said this phrase, it resonated to my mind because I am also behaving in that mode. So since then, somehow my soul is entangled with Yakir, and I am very grateful to be here. And I decided to do something which really will be interesting for Yakir, first of all. And this is what, after our first day of meeting, next day, Yakir gave me his book with this write-up. And that wasn't the only present which I received. This was personal present, but there was another one which is related with basic science. And this is sort of gift of the same sort which we were discussing yesterday and the day before. And I would like to spend a couple of minutes for this. This was related with time-dependent, with generally the question. We all know that superconductors can be described by wave function. However, how deep is this analogy of superconducting wave function with quantum mechanical wave function? That is not simple question, and even Ginzburg and Landau, they who originated this theory, and original theory was static. In static case, the relationship between psi function of Ginzburg-Landau and Schrödinger's wave function is more direct. And but when you will go to time-dependent problems, you will see that time-dependent Ginzburg-Landau equations are not similar to the Schrödinger equation. And because of that, probably the originators never were talking about wave functions. They were using terminology psi theory, and not more than that. So, and when we were discussing with Yakir told me, but Armen, if we will go ahead and use imaginary Hamiltonian, it will immediately become like Schrödinger type of equation. So, and that was, mathematically I came to that conclusion myself before, but I didn't know that Hamiltonians can be imaginary. And that is what I learned from Yakir. He said that in cavities, in some situations with quantum problems, you can have purely imaginary Hamiltonian. And this is something which is bridging, is setting up very, very interesting bridge between superconductivity in terms of time-dependent Ginzburg-Landau equation and and Schrödinger equation. We will talk about that a little bit later, but one example I would like to show why this is important. Next slide will show time-dependent problem which is being described in terms of Ginzburg-Landau equation, the equation which I just was showing. So this is animation. On this slide, this is psi function. At time equals 0, it is constant. Then we put current through it. Current is bigger than critical value, and it consists of 3 components: supercurrent, normal current, and interference current. And you will see now what will happen, how interesting will be this dynamics. Just let me click on it. Where is the page up? Let me see. Here. So psi function goes to 0. At some point it will reach 0 value, and current components are converting into each other. Total current is constant. This is one-dimensional wire. Very simple quantum mechanical problem or physical problem. Simple wire, and current is moving through it, constant current, but dynamics is complex. It's very complex, very interesting. And what is interesting that here we have a sort of measurement process when quantum entity Cooper pairs are interacting with normal electrons, and eventually psi function is getting damaged temporarily at this point, but then it comes back. And this is only one simple example we can solve using time-dependent Ginzburg-Landau equations. Many more complex problems, and in which case we have this kind of interaction between classical system and quantum system, and it is, for me, it is very interesting to include fluctuations and see how fluctuations are ruining and making irreversible coming back of superconducting state or quantum state. So unfortunately, I haven't had. Sure.
Why does it come back after the wire turn normal?
Well, that is what, because this is called phase slip centers. This point is phase slip center. Phase is jumping by 2 pi and relaxing, and then the system comes back. So it's periodic. It's very well studied system, yeah, experimentally and theoretically. So, but as I said, it contains very straightforward example of quantum classical interaction, and on the language, in the language of quantum physics. So I am very sorry I wasn't able to go deeper in this using this bridge, because laboratory life is not leaving too much time for theory, and maybe at some point I will get sabbatical and will be able to do more in this area. But what I did, I wrote a book which in particular contains this example also, including the code, and I would like to present that book to Yakir. Yakir, the same thing. Okay, happy birthday. Yeah, the book was dedicated to my teachers. It has dedication inside, and Yakir is one of my great teachers, so I am happy I can do this. Now, so what would be interesting for the audience and for Yakir, the talk will consist of 2 parts. Part number 1 is related with our laboratory activities. So we did something related to Aharonov-Bohm effect. Topic was discussed with Yakir about 2-3 years ago, before COVID. And COVID, of course, interrupted, and we spent more time with some other issues, not laboratory work. I will tell about that too. But I will tell about this, and all these topics will be covered. Then the second part is with superconductivity, because Shmuel called me and said that, Armen, I talked to Yakir, and he is interested to hear about room temperature superconductivity latest arrival. So we will discuss that in detail. That will be second part. I think. Okay, I'm sorry. Let me set this clock so that I would like it to tell me. Okay. So, so what is going on in our laboratory related to quantum science? This is a problem which was touching very deeply. Why cannot we detect Aharonov-Bohm field locally? We know that if we will surround it by a closed loop, there are different ways to do that. We will see it, the Aharonov-Bohm field and the Aharonov-Bohm effect. But why cannot we do that locally or quasi-locally with some quantum object? Which my belief was that quantum objects may be able to feel presence of the AB potential locally. Well, Yakir told me that it is probably hopeless, but nevertheless, he said that try, it will be very interesting if result will be positive. So I will explain how this works. So of course, this idea is sort of not very acceptable. However, suppose that we have superconductor. This is superconductor. We are cooling it down, and we have here superconductor setup. This is again result of modeling. So we set superconductor up, and this is a strip which we will put current into that strip. And if the AB potential is along the strip or opposite to the strip, it may be that in the dynamic case, and the dynamic case is when we are putting the current pulse, the dynamics will be slightly different when the current is along the AB potential and when it is against the AB potential. So, and what happens in principle to do that, you don't need to change the direction of the vector potential itself. Vector potential can be statically here so that we will not have electric field related with its dynamics. So what we will do, we will just reverse the polarity of current. So once we will give current from here to here, then backwards. And when you model that, the modeling provides this kind of pattern. And depending how long you will wait, you can in principle break completely. This blue color is normal state. These are flux quanta, Abrikosa vortices. So when it is parallel and anti-parallel, for the same time of duration of the pulse, you can have this picture, and you can have this picture, which is distinguishable by classical instruments. You can see voltage here, no voltage here, and the larger voltage here, big voltage here. So for that, we need a bridge. To have a bridge, we need to make it. So that was the task. And this was interesting for US Navy, and they suggested, they offered money for very skillful experimental groups, but these groups said that it is too complex experiment, and we are doing quantum computers, qubits, and so on and so on, so we have no time for that. So it was necessary for us to take the job, and we started to make bridges. So this is one of the bridges which we made from niobium-3 tin material, relatively narrow, but as I said, we need to put a current and then reciprocate its direction, in which case we shouldn't have hysteresis. because if we have hysteresis, hysteresis should be caused by Aharonov-Bohm potential, but not by the bridge itself. So it's turned out that we have, without any Aharonov-Bohm potential, we have hysteresis, and when we started to look at our properties of our bridges, and at that time it turned out that there is a big wave in superconductivity physics related with superconducting diodes, because using this you can make a diode. This is how it works. So you put sinusoidal current through the bridge, but you have voltage spikes, and here it is zero potential, and the average potential in this direction is not zero. So it is working like classical diode, but in superconducting material, which was by itself interesting for sponsors. So we were not the first who did this, but we were the first who raised the frequency to 100 kilohertz. Until that, it was for very low frequencies, like 0.1 hertz, 2 hertz, and we were able to go to 100, and it was published when we submitted to PhysRevB. It was January 6 when we submitted. In February 6 it was accepted, and it was printed also in February. So I never was expecting this kind of speed from PhysRevB, just because somehow our finding resonated with what was of their interest, probably. Then when we did this, we tried to understand how this diode works. It turned out that you can explain by modeling, again using time-dependent Ginzburg-Landau equation, behavior of the diode. So this is the bridge, and I now will click on it, and the dynamics will start. So this asterisk here, blue asterisk, is moment of time. So this is a current versus time. You will see. Let me do that. So see, it is starting to move, and at this point it will create some voltage. See, vortices will start penetrating through the edge, and that will build up voltage across the bridge. Then they are gone, and we are coming now to the reverse polarity maximum, and the vortices will try to enter through this edge, but will not be successful. So pay attention to the color. Color again is showing the psi function density, modulus of psi function. So see, they are trying but not able to go in. And then the process continues periodically. So this is one, this is second. So we have spikes only when vortices are coming from the top. Because this edge is weaker, for this process to take place, you need to have broken time reversal symmetry and broken inversion symmetry. So the edge is breaking, difference between edges is breaking centrosymmetrical arrangement, and magnetic field which is applied perpendicular, weak magnetic field which is applied perpendicular to the film is breaking time reversal symmetry. So because we understood this much, it was interesting. It generated a novel idea. Novel idea was, novel idea was, if that is correct, let's do the following. So from the top, vortices or flux quanta are penetrating themselves, but from the bottom, process is not successful. What if we will facilitate by injection, artificial injection of vortices, facilitate that process? So we were injecting the first one, and then that is triggering the whole train of flux quanta, which means that if this will work, then we will have some kind of valve, or like transistor, because transistor means that it is not going, but if you are applying something, you are making it go. So it will be analog, superconducting analog of transistor, which will be very useful for the same, say, quantum computers or circuits like that. Then it turned out that it really worked. So what we did, this is our laboratory-made device. So device is the following. This is just the real device picture. So this is major part of the bridge. So current is being put from here to here. And these are auxiliary leads. Through auxiliary leads, we will inject additional portion of spike of current, which will generate here the vortices, and then the whole bridge will become normal. It's turned out that it works, and I am showing it here. This panel shows with plus 50 Ørsted field and minus 50 Ørsted. You can have, without injection, in absence of injection, you can have dioding. So this is dioding and this is dioding. But if at this moment of time, I will apply current through these two leads, as soon as I'm applying, I'm getting symmetrical, see what happens, very interesting. So bridge is completely restoring its normal appearing voltage due to normal current flow, or due to existence of flux quanta there. As soon as we will stop current through the auxiliary leads, it will be gone, and again and again. So this was very interesting, and we gain in our device was about 3 to 4. It wasn't very big gain, but principally it is not too bad. So if you will have gain factor of 3-4 in the very first device, you can improve this. This is, by the way, lithographically patterned system. So again, we call this quadristor because it has 4 leads required for its operation. So with 2 auxiliary leads with small current, we were able to switch on and off much bigger current. So again, it immediately was this time applied, Physical Review Applied, I think that is the name of journal. They themselves suggested us to publish it there. So we submitted it by invitation. So and they published. They peer-reviewed, of course. It took longer, but it was. We addressed all the referees' comments and questions. So we are lucky this happened. So at that time, Andrew organized here a very interesting, I don't know, seminar or conference. And one person was Francesco Ghiazzotto. He was he made very impressive talks, and he has very good group in Italy. And somehow we made friendship remotely. And he was talking, among other things, about new material, rhenium-based superconductor, which inherently has built-in time reversal symmetry breaking and inversion symmetry breaking. So you don't need magnetic field, you don't need artificial symmetry breaking. So when we learned about that material, we said, why wouldn't we do that material? And Francesco also had his own interesting ideas, so we decided to submit a proposal which was about very sensitive, orders of magnitude better than existing these days in the world, single photon detector, and unfortunately, NSF decided not to invite us to write. After white paper, it wasn't accepted. However, we decided to keep things running and made these films nevertheless using our internal resources and sent them to Italy. So he was very excited, and his graduate student these days is doing something from that film, and this is our deposition system. So I will come back to it later related to room temperature superconductivity because it will be important ingredient of our plans. So this is a film which we made, rhenium-9 niobium, which has rather good critical temperature, and let's see what will happen with it. But we will do our own bridges from that material also. It is just we haven't yet had the chance. So now the next small part of our activity was related with gravitational waves, but I don't want to spend too much time on it because, again, it is published in Physical Review Research, and it is like, in very brief, it is two barbells attached to two squids here and magnetic field which is not moving. But when the bridges are moving, consider these guys as squids. So two squids, two gigantic squids, or macroscopic squids, I would say. Yes, they don't need to be gigantic. So when they are moving in opposite directions under the influence of gravitational wave, they are generating electric spike, electric voltage, electric signal. So we call this GEFEST because gravitational wave energy through magnetic flux energy and superconducting transducer goes to work. So and this is its sensitivity here. So this is not yet pushed to extremes. This is what was reflected in our publication, but I think that we have ways to improve it further and to compete. It is already competitive, but it can be improved, especially in view of yesterday's claim, which from John's report, we probably need to think about super-oscillatory approach to gravitational wave detectors also. We haven't yet done that, but it is necessary to think in that direction. So interesting thing came about gravitational wave detectors from Shmuel, because he called me and said, Armen, in Physics Today, on the back cover of Physics Today, this guy is made some very precise big G measurements and so on and so on. So I also looked at the journal, found the article, and contacted him in Switzerland. And he agreed to collaborate with us and to be part of our future proposals. So this is a very good collaboration. It would be very good because they are very skillful with mechanical parts. We are not skillful with mechanical parts of gravitational wave instruments. We know superconductive part of it, but not mechanical. So he will be very helpful. So, and the new building is coming soon, next year, probably at this time, we will be transferring the equipment there. So this is the old Bielefeld school. This is the new laboratory building. So I would like to express gratitude to Chapman administration, and Jeff told me that Yakir was very supportive of the idea to have experimental lab in the Institute for Quantum Studies. So probably Danieli didn't ignore that point of view, and I am grateful to both Yakir and Danieli for that. So we will be here, then we will have younger generation helping us, and things will progress much faster. Now, second part. So room temperature superconductivity, LK99, and so on. So let me forward because it is not too much time. So this is the whole history of superconductivity. It was very dramatic, actually, and these red lines are showing the breakage of axes. So from here to here, you see 10 years increments are 10 years. From here to here, I mean increments in time are here. So and then here there are 5 years, 5 years, 5 years, and here it was 40 years, 40 years. For 40 years, during 8 years, we reach somewhere here. And now we are moving much faster, and the same happens with the critical temperature. So here it is 30, 40, 50, but here it is, so 10 is the step, and here the steps are 50. So the axes are different. But what is interesting, there are two main mainstreams of superconducting materials. One of them I would call BCS type. Second, we will call non-BCS type, or better to say electronic mechanism, or electronic, they call it these days charge transfer super exchange. So this is electronics, mainly electronics mechanism. It is very interesting that YBCO materials, they were this charge super exchange, they reach this island about 150 degree, and stop there for a while. Then BCS superconductors start to do more progress, and I think that this was predicted by Ashcroft, and this has nothing extraordinary. It is only using light element, because hydrogen is a light element, and related phonon modes have very high frequency. Because they have very high frequency, BCS expression is showing that critical temperature should be high. However, the problem is here that we need very high pressure for that to happen. And when this was first reported in 2016, there was first international workshop in Italy, which we attended, but second we organized here. So these are attendance of part of them, not all of them, but part of attendance of that superconducting meeting. And the guy who was originator of that big wave is this Russian physicist working in Germany, Yeremets. And here he is at Chapman giving the talk. And this is schematically how this is working. You probably know it is anvils, then the diamond anvils you need to squeeze to very high pressures. So at that time it was 203 Kelvin. But then, and very recently, Dr. Zias from Rochester, he was able to rise the critical temperature to room, but that wasn't the major achievement. The major achievement was that this time he was able to reduce pressure to 10 kilo bar, 10,000 atmospheres. And 10,000 atmospheres is something which you can, in semiconductor technology, you can just use the interaction between material and substrate. That will be enough. You can using constraint generated by the substrate is able to create pressures up to not only 10 but 30. So in principle, it is possible to try to reproduce his results without any applied pressure using thin film technologies. And we were planning to do that. It is very interesting, the story is that because his first article in Nature on relative material was withdrawn by the editor. And nevertheless, Nature is publishing his second article on the same topic, because probably the reviewers found nothing suspicious or nothing wrong, as much as I know that they allowed external reviewers to come to their lab and watch how this material works. So it is still not withdrawn, and the activity related to that now is not as how to say, within the intention of researchers, because another material arrived, which is apatite, I think that is English pronunciation, but in Greek apatitos means, by the way, unconfirmed, unsubstantiated, so it's a little bit sarcastic. However, scientific name is oxypyromorphite. So it is this material, and you can make jewelry of it, and this is, it is interestingly known 70 years already, more than 70 years. So, so what was reported? The group is in Korea, and the first article was in Korean language, and it was submitted somewhere in March. So at that time, probably nobody paid much attention until they published in Condmat. So this is the material itself. So it is ceramic material. They said that what they did, they replaced one of lead by copper. So instead of PB10, we have PB9 copper. The rest is as I wrote. So this is the material, and you have force drop at above 100. This is now centigrade. Temperature now is not in kelvins, it is in centigrade. So, and it is coming down to 0. And what is interesting that they estimated their value of resistivity. And resistivity is in this 0 state. Resistivity, they wrote from the range 10 to the minus 6, 10 to the minus 9. 10 to the minus 6 by itself is 1 microohm per centimeter. For comparison, I should say that good conductor like copper at room temperature have that kind of resistance, 1 microohm. So, but this is nano-ohm going down to nano-ohm. So this is better than the best known normal conductor at room temperature. And this was the first signature which they reported. This is their second signature, which is like magnetic susceptibility and field cooled versus zero field cooled. And so you see it is going negative. Difference is negative as it should be. And different materials show different values. This one is 10 to the minus 4, but this is 10 to the minus 1. And this is relatively big diamagnetism. And they said that their levitated object, which we will look at it in a bit, is made out of this material. So this is the levitation creating material. So magnetic signature is here. Then other two properties, critical current versus temperature. It behaves as it should. So for lower temperatures, you have higher critical currents. For higher temperature, you have low. And the same related with magnetic field. So at room temperature, applying different magnetic field, this is 0 Ørsted. Critical current is big, then it is becoming smaller, 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 and it is quite symmetric, both here and here as it should be. So when I was talking to our potential sponsors and I told that maybe it is a little bit premature to consider this as enough evidence to support us, they said that what are you missing? Is something is absent there or something can be criticized? They said that we think that you should start working on that. So we got some money from ONR for this problem to be handled in our laboratory. But the news is that most likely government will soon announce on DARPA level big program in the United States related to this. And this is from that previous plot, how the critical current moves down with the field and how critical current goes up when you cool it. So of course this is somewhat smaller values for critical current or critical field, I would say, but this is 0.3 Tesla, right? It is relatively small, but the material itself, we need to distinguish between properties of material and properties of the sample. So if it is ceramic sample with granular structure and especially multiphase, and I have no doubt that it is multiphase, then critical values can be relatively small. The authors of original report are continuing to improve their understanding of what's going on. This is from the initial publication. I compared with the updates which they provided. See, initially they were thinking that conductivity goes on between lead and oxygen, but later they understood that it is between copper and oxygen, copper-oxygen chains, like very similar to what is going on with oxide high-temperature superconductors. And now I would like to spend a little bit time to discuss the criticism which is generated by other groups. So, and by us also, of course, but at the same time, see what they say you should do. You should take this substance, and this substance, and I mean these two substances, and solid state synthesis process will generate this one. However, arithmetics is not coming through because, see, final material is this one. It has 6 phosphorus atoms and 1 copper. But the only source of copper and phosphorus in their description is copper 3 phosphorus. how can you use 3 atoms of copper and 1 phosphorus and get 6 phosphorus and 1 copper? Where is the rest of copper? So it cannot, copper is not sulfur or oxygen, it cannot evaporate that easily at these low temperatures of synthesis. So something is here which is either not described, or they maybe are doing some selection from multiphase sample, I don't know, but something is not, and people who were repeating steps of original discoverers literally following their recipe, they were failing. So one such group was in India, and Dr. Avana, and I wrote him a letter that, dear Dr. Avana, because this guy's original group is so busy these days that they will not respond. So I decided to talk to people who try to reproduce. I asked, how can you accept this kind of situation with copper and phosphorus? And he said, your query very right, so nice of you, so. And he said that I myself wrote a letter to Koreans. Here is his letter. He's asking the same question. I don't think that he got any answer. However, despite there is obvious controversy, he thinks that this is Avana's group is here. So see, despite there is arithmetical discrepancy, he says that no superconductor is absent, but the synthesis wasn't done well, or something is not accomplished as it should. So these are other groups you can see, mainly from Korea, India, China, and Korea. They have also patent filed. And the last thing which I learned from them is that they change the status of their company from research to manufacturing. So probably they are absolutely aware that they are on the right track. And United States is only one person, solely US, this guy. And one is in group with Spain and Germany. But experimentalists are mainly negative. But I will talk more a little bit about that. For example, this one. Look, this is X-ray diffractogram. And from one of the critical articles, I don't remember from which one, but look, this violet is the observation experimental, and they think that their observation is matching what it should, which are these red lines. But indeed it is not. For example, this line doesn't have, what about others? They have so different pattern. They think that they reproduce, but I wouldn't call this reproduction of the original material. And this other one, this is, unfortunately, Koreans didn't provide any elemental analysis data. So this is, again, by the other group, which is claiming that we are not able to reproduce original findings. But let's see, what do they have here? They have copper, which is 1, but we know that phosphorus should be 6, and it is not 6. So can we believe that criticism is serious? I am not thinking that the criticism is serious. This is a very nice book called Cold War's History of Superconductivity, wrote by George Vaisant. This is famous guy. And this is talking about, in particular, the discovery of YBCO superconductors. 5 minutes, yeah, I'm getting to end. So he, at the time when Bednarz and Müller discovered at Rushlikon their material, in the neighboring door, there was another physicist who later became very, how to say, authoritative person. He wasn't able to reproduce their material next door because they were using liquid passage to based synthesis. He was trying to use solid state, and he wasn't able to do that. So reproducing results, especially if the guys are doing that, Korean guys I mean, for decades and eventually got to what they want. And this is another explanation which we did in our lab. So this is very interesting story. This is niobium deposited on sapphire. This plus thin layer of niobium deposited on sapphire, and on top of that we deposited lead. So these white bulbs are lead on top of niobium. And see, lead transition temperature of lead is 7.2 Kelvin. And we see that at about 7.2 Kelvin, instead of going down, it is going up. So temperature tells that inevitably it is related to superconductivity. But instead of going down, it is going up. So, and this is actually what is it doing, the same transition when it is going up, but zoomed and at different fields. So it's definitely going up. And if you will go ahead and use this film in magnetometer and measure, you will see that it is behaving magnetically as superconductor should do, but only in the field of 300 Hz. If you will go to 1000, instead of going down as it should, it will go up. So this is telling very good example how a multi-phase system, so this is two-dimensional example of the three-dimensional ceramic when the superconducting inclusions can be surrounded by different phase. Instead of going down as resistance should do, it will go up. So you should always keep in mind that this all is not very straightforward. And theoreticians are much more, so theoreticians make calculations using quantum physics, quantum mechanics, density function of theory or something similar, and see majorly supporting that this could happen. In case of Diaz, Rochester group findings, they were almost unanimously telling that it is theoretically impossible what Diaz is reporting, but in this case they say that it is possible. So, and this is our plan, how we are planning to do that. We would like to just use, this is our deposition system. It has many magnetrons in a row. We can use them simultaneously. So we would like just to take copper, lead, phosphorus, and regulate the fluxes and put them on the surface of the substrate using the proportion which is required, and then bake it and see what we will get. We may have very pure phase which will superconduct right away, and that is what we have also very good feedback for elemental microanalysis and for X-ray diagnostics. So,
how low did he face you? How low?
How though? I think that month or two, I would like, one problem is one of the targets which I need, they said only September 6th it will be available. So we need to wait until target will come. But then immediately we will do it. So, and then I would like to finish with this. No, but this will take 5 minutes. So this is very interesting story called the level of noise. I asked Shmuel, does he know about that, and a couple of colleagues, they don't know. I will just start but not finish. You can later look for that yourself.
There's a meeting called in the Pentagon. The chiefs of staff all come to the meeting, and there's a president's representative there, and there's this big table. In the middle of the table is this plastic wrapped bunch of burned junk, and it was sealed up airtight, tied off anyway. And the president's aide tells the assembled scientists and professors who've been called in from all the United States and the generals, he said, look, I know you're not going to believe what we're about to tell you, but something extraordinary happened last week, and we need your help to solve the mystery. He said, we have some of it on film. We were testing this young fellow's device. He's kind of a smart aleck, but we were testing it last week with him, and here's the film we took. And so they opened up the curtain, and the film starts. And you see this young, kind of red-haired, freckle-faced scientist looking smart aleck, really a bright genius type. And he's got this little chest pack and a backpack and a little belt, and he's standing in front of some of the generals there in a football stadium. And he reaches down, and he pushes a button, and he lifts up off the deck 2 or 3 feet, and just stands there in the air. Nobody says a word in the office there in the Pentagon. They're thinking, wow. Okay, so he's been lifted up a bit. Then he pushes another button, and he rotates sideways and lifts up about 40 feet and takes off, flies around the football field and comes back around, for a low pass over the generals, everybody ducks, and there's a puff of smoke. Quick explosion, he nosedives into the deck and dies, a ball of flame. The package on the table holds the remains of the guy's instrument, what's left after the fire melted everything together. He said, gentlemen, he died before he told us how he did it. This guy doesn't work for any government. He's just an individual. He doesn't have any university grants. He's just an individual, and he did this. Now, you've got to figure out how he did it. We've got his apartment. We've got his library. We've got his lab. We've got everything. You go and take his notes apart and figure out how he did this. Well, everybody runs over a big gaggle to this guy's apartment. They look through his library. He's got chemistry here, physics here, philosophy, ancient mysticism, everything. And he's got a lathe room and downstairs in the second floor area here. And then he's got over here, he's got biochemistry and all kinds of stuff. And they said, could one guy have read all of this? And they start looking through some of the volumes, and there's notes, annotations in the margin. Well, where are his other notes? Couldn't find them. Weeks and months passed as they puzzled over how he did it. And groups all over the United States, for like Martin Marietta and some of the other larger corporations, had scientists gathered together trying to figure out how did he do it. One guy was out fishing, one of the scientists, and he's throwing his line into the water. And as it hit, ripples went out, and there was a swirling vortex next to a rock. And he saw how the splashing water moved some twigs that came together, pulled in by the vortex and stuck together. He says, I've got it. I understand gravity now. They went running back, and a month later, they rang the guys at the Pentagon and said, we've done it. It's 30 feet in diameter, and it's about a foot thick, and it weighs 15 tons, and it only moves off the floor an inch, but we've got anti-gravity. Well, the Pentagon said, get your notes, get over here quick. Everybody is reassembled into the Pentagon in the same room. They show the film of the test to all the other guys who weren't there, and they said, wow, fantastic. The guy that called the meeting said, gentlemen, I want you to meet someone very special. Curtain opens, and out comes the red-headed scientist, the dead one. And they said, what is this? They said, well, he's an actor. He never existed as we told it to you. We had to remove the noise level from your mind to say that it is possible to get you to work on it. Now, I tell you this for a reason. Two streams of events have been following the UFO circumstance, the real alien or fallen one's chain, and the one where the noise level has been removed in certain scientists' minds to get them to develop this. We have developed anti-gravity. I was recruited way after they got it for the first time because I came up with a method of powering a saucer craft using an ionized air plasma, which I'll explain to you later. In that program, under Dr. Teller, I was sent down to Australia. And so I have been privy to things you would never see. You would never, ever see. And I'm going to show you some of those things as best I can recreate them today so that you'll understand that mankind has, on his own accord, done some of this.
Okay, so this was from Ginsburg, included in his book. So I am almost done. And one more thing I would like to show you, which is telling why we should believe in this finding. So there is a big difference because some people say that this may be diamagnetism but not superconductivity. I would like to show you what is the difference between superconducting levitation and diamagnetic levitation. So just very short movie. This is diamagnetic levitation.
We have here four magnets side to side.
This is my voice.
In this manner so that the field in the middle is the weakest. And now I will suspend pyrolytic graphite. Okay, so it is suspended. It is in local equilibrium. A little bit, if I will move it, see, it is flying away. And this is very different from what Koreans did.
Okay, now what Koreans did is here. You probably have seen this, but look what is difference. It will not fly away. The diamagnetism, it should be this local minimum of magnetic field in the center, it's keeping it there. It is not anything which is tying it, but this is what Koreans sample is doing. And it will not fall down, as you will see, it will fall down, and then See, it is jumping up. So this is real diamagnetism, the real superconductivity versus diamagnetism. So this is another superconductor. See, this is Möbius strip. So it can be suspended from underneath of it. So superconductor not only levitating, but it is also tied to the magnet. It will not leave the magnet. It is underneath and not leaving the magnet. So that is, if you know that, you will never say that it is diamagnetic, what the Koreans did. So this Möbius, levitation at room temperature, I have a small kit. So this is my second present to Yakir. Just you can levitate. Inside you have the two pyrolytic graphites. Yeah. Here they are, and you can, what I just did, you can do. Here is a magnet. Mm-hmm. Don't put near your credit cards because it will destroy them. Yeah, and here, this is it. So if you will put these guys and bring it close to it, it will levitate.
Thank you very much.
You're very welcome. So, and the last click. So, to Yakir's 100th birthday, let's have this at Chapman without any liquid nitrogen, just room temperature superconductor levitating, so that the students will be attracted, and we will have celebration of superconductivity and quantum physics here. That's it. Thank you. Okay.
I haven't read any of the original Korean papers or the follow-up papers, so what I'm saying is not a statement, it's a question. I read the editorial of Nature today, and some recent 7-hour-old news about this, and they all seem to be very conclusive against superconductivity. And as far as levitation is concerned, they note that there is an edge which sticks out also in your movie. And for some reasons, the expert says that this is a clear evidence.
Yeah, I can address that. Yeah, I understood.
So what is your? It's a question. I'm neutral.
Yeah.
But what is your reaction to this conclusive, overwhelming opinion? And let me add one thing: is that the authors, the Korean authors, were asked about all this, and they did not respond.
I would say the following, that I know that example, and superconductivity and magnetism in solid states may be very close to each other. A little bit that way, a little bit this way, and instead of magnet, you will get superconductor, and vice versa. And what they are referring to is that you can have some kind of magnetic material which will, if we will go back, it will be just instead of, where is my, instead of flying like it is flying, it will stick vertically like this. In principle, that is what two groups have obtained. But like in mathematics, as soon as you have one counterexample, any argument that this is true, it will not be correct as soon as you have one counterexample. So if we will consider this as a mathematical counterexample, the theorem is proven. So if they are cheating, that is another. In principle, for example, you can cover this, you can have configuration like this, and here underneath, if you will make some weak magnetic area, in principle, you can mimic something like that, but that will mean obvious cheating. So if the answer is the following: if they are not direct cheaters, then all the evidence we have that they got superconductors. Yeah.
Yeah, thank you. I just wanted to comment that if I understood what you said about the Ginsburg-Landau equations, when you said I want to take the form as Schrödinger equation with imaginary Hamiltonian, am I correct? This is what you wanted
No,
to say?
not necessarily.
Slide, so what was that imaginary value Hamiltonian?
No, I don't want to work with Hamiltonians. I would like to work with Ginsburg-Landau equations, but to do more to relate it with the measurement problem. Measurement problem, in which case, one thing, since you are asking, I will tell you. When you consider without fluctuations, when superconductivity dies, psi is becoming very small, but it is on the level of 10 to the minus 44. It is still there. It is not completely dead, but I think that it will be completely dead if we will consider fluctuations, in which case we will have closer relationship with real physical measurement, which nobody did, and I would like somehow to tap into that, but have not yet had a chance.
Yeah, but I must say that if you consider the GL equation, and you wanted to take the form with imaginary value, the Hamiltonian, I must say that you said it psi. Why you don't say it is a wave function? Because in that case, it will not be a wave function. It will not be any interference patterns. It simply will be a modified version of the heat equation.
Oh, yes, that is what they were considering until Yakir told me that Armen, instead of considering it as a sort of heat equation or diffusional equation, you can consider it that as a Schrödinger with imaginary Hamiltonian. So that is what I wasn't daring to do, because I didn't know that imaginary Hamiltonians are allowed in quantum physics. But Yakir told me that they are. And I am sorry, I am not, I tried to find some literature. I didn't have much time, but I wasn't very successful in finding this kind of works. Yeah, but that doesn't mean that they don't exist. They should be somewhere there. So we should get there at some point. Mm-hmm.
I think Adi, did you have your hand up?
Yeah, on this LK99 context.
Yes.
So what would be a definitive proof? The Johnson effect?
No, I think that if somebody will reproduce it, it will be proved, because they provided enough evidence that it is superconductor. The major thing is that others are not able to reproduce. That is a major hurdle.
And the number of failures of attempts to reproduce?
As I said, these people spend, according to, in the Korean, there is an article in Korean, we use Google Translator and translated that Korean article, and it is, in that article they tell how many years they were doing this, all their failures and so on and so on. So if, of course, when you are running behind the front runner, you have benefit. Yes, you can make it much faster, but you still need to spend comparable time. It is, in YBCO case, it became very easy to reproduce, and at that time, people were telling that even housekeeper can do that in her kitchen, this material YBCO. But as I said, the first one, which original Bednarz and Müller one, the person next door wasn't able to reproduce. So, but it really was superconductor, and he wasn't able to reproduce. Until YBCO arrived, YBCO is much easier to reproduce than lanthanum strontium original, which Bednarz and Müller discovered. So I think that as soon as they will reproduce, that will be it, I think. And why these people are not telling the whole truth? From my point of view, it is multi-phase sample. We need to get to the right phase to get it, we need to extract the right phase from the mixture.
When you see 10 to the minus 9 ohm centimeter,
Yeah, it's
such a small number, could it be an artifact coming out of a short somewhere?
It depends on how many. In one sample, it can be artifact, but if they made it on many samples,
How many
it's
samples
They don't describe too much. You know, they are sort of, they are not physicists, I would say. They are more chemists than physicists. But sometimes science is being done by dilettantes. They are dilettantes in superconductivity, but they know a lot. They know a lot, they are skillful. It is not that they are just, you know, amateur persons. No. This is respectful group. So we need to respect, first of all, and give them some respect, and then only start criticizing is easy. It's very easy to criticize. Right?
Andrew?
Yeah, I wanted to make a couple of comments about both of these room temperature superconductivity examples we've been talking about. So I know less about the LK99, but my understanding is that the material is not particularly exotic, that many groups can in principle reproduce this material relatively quickly, and indeed the results that have been trying to reproduce it so far have failed. But the point I want to make is that the material itself is not particularly exotic. It should be relatively straightforward to fabricate it. Maybe I'll pause and ask you to comment on that before I go to my next comment.
This arithmetics, Andrew, this arithmetics is raising obvious question. How are they balancing? How are they taking 3 coppers and 1 phosphorus and getting 1 copper and 6 phosphorus? This is very, very simple question. And our critics, they have a group, they tried 10 different recipes. And they say, we tried 10, but that doesn't mean that 11 will not give you what. Yeah.
Yes, it could be there's simply not enough information given.
Yeah, I also have some information that MIT delegated 3 researchers to Korean Institute to see on site what is going on, but I haven't heard of any report about that.
So then in your attempts to reproduce this, then which recipe are you going with?
You should be, that is very good question, Andrew. The matter is that this material is very hygroscopic. One possibility was to use, using copper, applying copper and applying lead is not a problem, of course, right? Then phosphorus is what is creating problem, because if you will take P2O5, you can take P2O5, which sublimes at about 300 centigrade temperature. Then it is unfortunately crazily absorbing water. And when it is absorbing water, it is becoming phosphoric acid, H3PO4. And this phosphoric acid very aggressively reacting with metals, all my $500,000 chamber will be ruined in one. As soon as I will open it to air after deposition, all the walls will become acidly corroded. So you should be very cautious. What are you doing? How are you doing? So I am trying to get copper. There is copper phosphorus or lead phosphorus or copper phosphorus. That is solid target. So then you will not probably have this. But still should be very cautious. How are you doing that? So and then oxygen problem. Oxygen problem, in principle, we have also ion gun, which can bombard during the deposition. You can bombard by oxygen ions to get it saturated by, because see, it is almost completely oxygen. Out of 41 or so atoms here, 25 is oxygen. So it's mainly oxygen, like YBCO. YBCO has same thing. It is so it has about 7 oxygens and 6 other elements. So majority is oxygen, is there and here.
So I'll just make one very short other statement about the Diaz results. So I have been following this very carefully, and I just wanted to comment that there have been a number of very serious allegations of fraud raised in his case. Not only plagiarism,
that's true.
Not plagiarism, data fabrication, data manipulation. Not only was the Nature paper retracted, there's an upcoming PRL he published that was also retracted. So there's very serious cause for concern about this research coming out of this group. I just want to caution you that it's quite possibly this is all fraud. So be aware.
Yeah, that's true. Yeah, of course you should be cautious. Yeah, I agree with that absolutely.
I think we're going